Hello, and a very warm welcome to today's Cell and Gene Therapy Insights webinar titled Chromatographic Modalities, Buffer Selection and Other Considerations for the Enrichment of AAV Product. I'm Abby Pinchbeck, an editor at BioInsights, and joining me today is Žigon, who will discuss paramount considerations for scaling up and present a case study using a design of experiments approach for buffer selection and robust preparation for improved separation of empty and full capsids. After the presentation, we'll have a live Q&A session, so do feel free to pose your questions to Rock using the Ask a Question box at the bottom of your screen, and we'll try to get to these during the session. I'd also like to draw your attention to the Resources tab on the right, where you can find more information on the topics covered today. Now I'd like to introduce our presenter. Žigon is the head of the product application area for AAV and adenovirus in the process development department for viral vectors and vaccines at Sartorius BIA Separations. He has 6 years of experience in the field of downstream bioprocess development, leading gene therapy projects for clients, resulting in processes for clinical phase 1, 2, and 3, and market supply. He holds a master's degree in molecular biology from the University of Ljubljana. So, without any further ado, I'll hand over to Rock to kick us off with his presentation.
Thank you, Abby, for this introduction, and I would like to welcome you all to the and thank you for joining the webinar. So to start the webinar, so really we want to focus on what are the challenges in our AAV purification. So to have some background as a setup, in each adeno-associated virus downstream purification, one of the key steps is really the enrichment of full capsids. Now, for achieving those, we have two options. We can go with ultracentrifugation, which has its limitations regarding to the scalability, and the another approach, which has the scalability, is using the different anion exchanger chemistries, but the problematic part here is really the charge differences. And since there's really such a small differences in the empty and also the full particles, those should be accounted in the anion exchanger chemistries. Now, the aim, let's say when a typical client, let's call it, come to us and he gives a statement, we desire less than 20% of empty capsids, high recovery by PCR, and stepwise solution approach. This is a reasonable, let's say, reasonable goal, but really the questions that we should ask ourselves is, how do I adapt my process to account for different serotype differences? And then also just accounting those 20% of empty capsids. So what are really the analytics that I should use and that really distinguish between the different AAV subpopulations, because we know there are not just empties, but also other subpopulations. How will my process be also controlled to allow the step washes and go from linear to step washes? And the third paramount thing also, how is my process, how is my impurity clearance and impurity removal in regards to the recovery? So in Sartorius BIA Separation, we like to look at the things from a holistic approach. And so we strive to achieve the highest purity of functional and potent AAV, accounting for all steps from upstream to the downstream. And that brings us to really, so having this in mind, this statement that we account for everything, the key thing here is really that we understand the process. Therefore, although today webinar, let's say it's aimed towards the polishing step and how to enrich our AAVs, we will go through all of the critical parameters and all of the critical steps starting from, so we will still focus on the downstreaming part, but upstream is also a big part of it. And we will really see the pre-capture, the capture step that is done on our SO3 column, the polishing step that we use 3 columns in our toolbox, and also the final formulation. So here on this slide also there is a further reading of a paper we published that you can see later on, but I think it's best to begin and start with the topics that we'll cover today. So we'll start with the pre-capture step first, where we look to different approaches. So one is the clarification of the lysate, and also then the screening of the TFF membranes as one of the options for pre-capture step. Then we'll go into our capture step, which is always done on a strong cation exchanger of SO3, and we'll see two different case studies on such capture step. We will then move to the polishing step to present our three enrichment columns, so Simultus QA, Prima S, and Prima T, with also one case study. Then after that topic, it will follow with analytics. So we will see based on the polishing steps. So we will look at the purity of the product, the percentage of full, the genome integrity, its mass and charge differences, but also based on the two case studies. And lastly, we will touch upon the scaling up. So what are the critical parameters that we should look and have also control over. So without further ado, the first one is really the pre-capture step. And this is, I would say, here it's where we see that the downstream starts. So really, one of the first things that you do when you have a harvest, it could be supernated, it could be lysate, but there is always some clarification that it's needed. In this case, I'm showing the AAV 28 from HEC 293 suspension cells. It's a lysate material, and the idea was here testing two different filters from Sartorius portfolio, so SartoClear DL75 and also the SartoPure GF+, having the constant flux and really the parameters that we should consider. And also when you're doing screening, you should define those. So one is what is my filtrate throughput, so what is the capacity of the filter. Second one, how is my turbidity reduction looking? Of course, one of the most important parts is the recovery. So you really want to have control over the recovery in the first steps, because the more you lose in the starting values, the less you can operate later on in the following steps. So really high recoveries in the first steps, and also all sequential are really paramount. And of course, as mentioned also in the beginning, reduction of the process-related impurities is also plays quite an important role. So the two graphs representing here, if we focus on the left one, we see, let me just bring up the pointer. So on the left one, we see the total throughput of the two filters, and we see that we have approximately a third higher throughput, so a third higher capacity obtained on the DL75. We have also better turbidity reduction, assuming that they are normalized to the similar pressures. So the depth filters also work in such a way that you have to maintain not only turbidity, but also pressure should be considered. But then on the right side, if we look at the same two filters, but the different parameters, so how is my protein reduction looking? We were using the Bradford assay here. And for the host cell DNA, so residual host cell DNA, we use the qPCR method aimed at HEC 293 cells. And also then the line above represents what is the recovery of my filtrate. We see in all of the cases that the DL75 it's superior to protein reduction, as well as to the reduction of the host cell DNA. But we do see that we sacrifice, let's say, short of 10% of vector. Now, in my case, I would definitely repeat those results and see if there is a trend of lower recovery, because as I said, the recovery is something that it should be a drive, and you should maximize your recovery above 85% in each of the steps to get a, let's say, approximately 50-fold recovery process-wide. So really here, it should be a consideration of if recovery could be increased. If not, I would go all things considered still for the GF+. Following and still staying on the pre-capture step, so we have multiple ways that we can prep our sample and then load it to the cation exchanger. And one that it's, let's say, common and also industry standard is the TFF. When we're working with monoliths, it's not really the concentration part, but we're using the TFF as a pre-capture step, so also to reduce the impurities level. And here, again, on the AAV28 lysate, we screened two different chemistries, the PS and the hydrosart, and we were observing the total vector genome recovery by PCR and the protein reduction by Bradford. In case of PS, we see that we are losing some of the vector at the 300 kilodalton mark, so we have approximately 60% of vector in the flow-through. We have a bit better recoveries at the 100 kilodalton, but reduction of proteins is lesser compared to the dose obtained at hydrosart, where we have basically full mass balance or full recovery, and also we intend to switch from 100 to 300 kilodalton because we get a better reduction of proteins. If we would be comparing those to the PS membrane, we increased approximately twofold. Now, one thing to really emphasize here is that different serotypes will behave differently. So one will allow 100 kilodaltons, other will allow also 300 kilodaltons. So I really consider that you should screen all of the different cutoffs, but not only the cutoffs, so also different manufacturers use different standards. So 300 kilodaltons will not always behave the same using the different manufacturers. So this is something that should be screened for every sample. Once the pre-capture is really done, we advance to the capture step. So this is really, with the capture step, we achieve successful binding of the AAV, and also at the same time, we want to have the concentration factor in there and removal of the impurities, largely those host cell DNA histone complexes, and also the HCPs, which are present either in the flow-through fraction or the CIP, so cleaning in place, which is washing the column with the 1 molar sodium hydroxide. So the cation exchanger, since it's a strong cation exchanger, it means that it binds positively charged particles. So in order to bind the AAV, which has a PI of around 6 to 7, so in order to bind it and introduce the positive charge onto it, you usually bring down the pH. So we go with the acidification method, and that also serves later on. If you go into the regulatory practices, you have to control your process and show the virus removal of the model viruses. So this is also one thing that is quite common as a viral inactivation method. In essence, so the SO3, what are those? It's their main advantage of the SO3. So binding capacity is really dependent on the sample preparation, and we will see that on the following slide, where we have a case study how those capacities differ depending on the approach that we take. Also, it binds any serotype, also the chimeric variants, so really it covers the entire range of the AAVs. Sample loading is also done at higher conductivities, which prevents, let's say, capsids that are more prone to aggregation, like AAV2. So we could load at elevated salts and also get then the better control over our AAV. Effective pH range is from 3.5 to 5. And as with our all monolith columns, the flow rates are usually 1 CV or higher, with recoveries about 85. So from small scale also to the larger scale. Unique also to the monoliths, they are reusable, so it sustains the cleaning with 1 molar sodium hydroxide, so it supports multiple uses. What are the points of optimization on the cation exchanger? So usually we work with buffering system, so anything that is in this acidic range, we increase or decrease the salt concentrations during the loading, or also during the eluate, and also the pH is quite an important factor. In this case here on the chromatogram, we use the pH 3.5, but also you can go with a higher pH, so around pH 4, depends again on the serotype, but definitely you run the linear gradient, see where your vector occurs, and then adapt to match those conditions. As mentioned in the previous slide, so here I'm showing the case study done on AAV9 serotype, which shows 3 different approaches of the pre-treatment before the SO3. So the first one is straight acidification, so meaning just we are adding in the concentrated buffer to bring down the pH to 3.5. Usually during this stage, a protein precipitation occurs, which also serves as a cleaning agent. You filter out the proteins which are precipitated, and then you load it to the column. In 2 other approaches, a TFF step is done before the actual acidification, so to really, as we saw on the second slide, to remove those proteins accounting on the 300 kilodalton unit. And the third approach is also addition of the nuclease, and in Sartorius BS separation, we like to operate with salt-tolerant nucleases. Why? Because really it weakens the association with the DNA and the protein complexes, so it's easier to then to cleave and better degrade the DNA, which are at those high salt environment. We can see also the effectiveness of the process if we're comparing the AAV peak versus the CIP peak. So the SO3 column really works in such a way that it binds everything to it, and the capacity is therefore limited with the amount of proteins that you also have available, so total amount of proteins. And in case of acidification, where we have just the precipitation part, we still see that we have a high range of impurities, but this ratio of AAV versus CIP really comes in favor when we have also the nuclease, where it's more or less 1-to-1 ratio, and that also then affects if we go down below. So how the capacities are looking, we increase approximately a log difference, so 10-fold difference from acidification to the having TFF coupled with nuclease, so increase a 10-fold capacity per milliliter of column. Also, what we achieved for the proteins for the protein removals and the acidification only, in this case there was barely none removal. However, we do see 2 log removals for the pre-treatment, or even 3 logs then when having also done also processed by an SO3 column. The same holds for the DNA. So we do see from 1 log to 2 log removals from having the pre-treatment and SO3, or approximately 1 log or a bit below with acidification, just as a pre-treatment step. So really, how you prepare your sample will define also your outcome, and the more clear and more pure the sample is, that it advances to the next stage, the better product it will be. Another case study that we performed was comparing the affinity approach versus the SO3 process, and we've done 2 repetitions per each set, so 2 runs of affinity and 2 runs on the SO3, and those were then expressed as seen here on the graph representing the process recovery, which by bars it represents individual step recovery. So we have steps of clarification, TFF, load preparation, capture eluate, and QA eluate, and the one on the left side represents the SO3 process, whereas the one on the right side, so more of a dark gray, represents the affinity recovery by step. And as well with the lines, we do have then the process recovery, so meaning accounting all of the steps. So what am I left after the TFF, going to the load preparation, and so forth. So really having the total mass balance in the end. So what can we see is that for clarification and TFF, we are having the same values. Why so? Because we use the same approaches for both. So meaning the TFF, so the clarification and the TFF were exactly the same for the 2 processes, but then we divided into 2 groups. So half of the material went to the affinity column, half of the material went to the SO3 and was processed there. We do see slight differences in the load preparation. Regarding the capture eluate, they were both comparable in the process recoveries. But then one thing that really I want to also emphasize here, and it's really take away message from also this presentation, is that we should look holistically, so everything from start till the end, because here is really where the majority of differences occur. And this is also something that you will see later on when we go into the polishing step. So how can I prevent, let's say, aggregation or some complexation or a difference in my AAV? So I want to track the entire recovery, not just step recovery, because here we really see close to twofold difference on the SO3 approach versus the affinity approach if we go to the QA, and that brings us also to a total of 10% difference from the affinity, with 30% process recovery and 40% on the SO3. So those 10% really plays quite an important role when you have a large batch of material. So it means more doses could be achieved from the same batch. Aside that, so not just the recovery, as said, importance is the purity of the product. So we really strive to get the most pure product. And again, we were comparing the SO3 versus the affinity for residual host cell DNA, residual plasmid DNA, residual host cell proteins, as well as the removal of endotoxins. Each of the steps, individual steps, so TFF, then the capture step, SO3 or affinity, and then the QAs following those two approaches are color labeled, and they are all showing so what is the logarithmic reduction on this individual step, whereas above each of the columns we do see the total, so overall removal expressed in logs. So what can be concluded from the host cell DNA, that two processes are comparable. The same could be said for the endotoxin. Slightly higher is seen on the plasmid DNA in favor of the affinity, but I would say all of those numbers are really within the range of the error of the analytics. So there were no statistical significance between them. One was, however, this was the HCP. So in all of the cases, the cation exchanger increased approximately half log more compared to the affinity. So really, importance of the assessing entire downstream process yield and not just the individual steps. Still having this in mind, so how we prep from affinity to QA. One thing that also we've done on a case of AAV2, we looked at the physical titer versus the physical titer measured by PCR and infectious titer by effectivity tests. And we used the different pHs that are usually done during the downstream processing. So pH 9 will come later on when we use the anion exchangers and use it for enrichment of the full capsids. The neutral stage for the loading of the affinity material, and then the acidic pHs for the, let's say, elution on the affinity or elution on the SO3. And we do see, so if also we account for the differences and the variances, we do see that the physical and infectious titer, when we are at the 3.5, it does not differ, so everything is within the boundaries, but there is a trend of decreased infectivity once we exposed our AAV to pH 2.0 when it's incubated overnight. So definitely there was a drop in the infectious titer, and this is something that I advise that you always be above 3.5% mark of pH unit, where we see that the AAV is quite resilient in those aspects. That covers really the pre-part, so really the pre-capture step and the capture step, and now we will focus on the webinar's main thing, so enrichment of our product. So we will look at the polishing step, and the first one we will go through is the simultaneous QA. So the QA is a strong anion exchanger, and really how dilution is performed. is that we're using the ascending salt gradient, and based on the differences of empty and full capsids, based on their charge differences, the empties will elute first, followed by the full capsids, and then we always see, not always, but in the majority of cases, we see also the third peak, which we label as damaged. What is really, let's say, the properties of the QA? It supports high binding capacities, so usually more than 2E14 vector genome per milliliter. So this is vector genome per milliliter, and the sample that we're using here was 30% of full capsid. So if we express this in total particles, usually we are in around 6E14, in some cases even 1E15 vector particles per milliliter is seen as a capacity for the QA. Again, also it binds all serotype. The sample loading is done at lower conductivity, so around 2 to 5 millisiemens, depending on the serotype, and the effective range is from 8.5 to 9.5 of pH units. Points of the optimization for the QA, usually we screen for buffering system, its concentration, what are the LO and salt, what are the pHs, and also the presence of the magnesium. Now, here on the left side, we have a chromatogram of how an AAV8 SO3 looks like. And later on, we will see also the Prima S and Prima T. Do keep in mind that we're seeing the same sample, so say sample at the same loading rate was applied, but you will see how it differs really from monolith to monolith. For the point of optimization, really on the QA, we have to account that there will be differences in the serotypes, so the AAV2, AAV9, AAV8, or any other serotype will behave differently, even sometimes within the serotype itself. So depending on what is your genome in there, so your target, it also might behave differently. So really, there is not a platform process, but with small tweaks of the process, you can cover quite a wide range, and then you adapt your process to match the conditions for your exact product. Another important parameters are the pH. So here we can see how it differs from going from pH of 9, going to 10 and 11. So the same thing that we covered before with the acidic pH exposure, so where we saw that the infectivity drops at pH 2.0. The same thing occurs also when we are going into alkaline conditions. And one thing that also shows us that is we usually see a decrease in the area of the full peak, and this third peak, which is associated with damaged capsids, becomes more evident and also higher in regards to its area. The third one is also really the magnesium presence. So we know that the magnesium plays a role in the keeping the integrity of the capsids. So it stabilizes the capsid itself. So no magnesium present in the sample will give you a different profile as those where you have the magnesium present. And this is usually all of the capsids that are here. So all of the degraded AAVs, damaged aggregated AAVs will move to the earlier site and elute as a single fraction seen here. So whenever we're doing any kind of optimization of the QA or any other polishing step, the parameters that we want to maximize and control are really the vector recovery by PCR, having the percentages of full AAV, so to really have a better, the highest enrichment possible, resolution between the species, so the empty, the fulls, the damaged capsids, and also all of the other subvariants, and also retention on the column. So the idea is that you want to have it that it elutes the latest possible. That means that also if you go with a dilution approach, this could mean a difference from 10-fold to 50-fold dilution, and especially in the manufacturing. So in the GMP area, you don't want to increase your volume from one step to another, so it should be reduced. Therefore, if you're having later elutions, means less of a dilution of your process. again, returning to this idea of affinity, so we have a lot of clients that are using the affinity column, and then they are using our QA for the polishing. And we saw that they were struggling when keeping the consistency of the runs. They were expressing that different profiles were obtained. Sometimes even peaks were omitting. The third peak was quite more prominent compared to non-affinity approaches, and therefore really we were trying to mimic those conditions. So here what I want to also present is that usually the affinity approaches are using the citrate buffering system for the eluate, and the citrate also has chelating effect, so it is chelating your magnesium ions, and before we said that the magnesium ions are needed for keeping integrity of the capsids. Therefore, the different amount of the citrate will also affect your chromatogram on any of the anion exchangers. And here is really an approximation, so it depends how you are fractionating your affinity eluate. So do I start from here to here? Do I collect just the peak itself? Do I take it for 3 CVs, 5 CVs? It will depend how much of citrate you will have then on your QA column. And on the right side, we express those in millimoles of citrate that were bound to the column. And we see if there is no citrate present, we see, let's say, a textbook QA looking peak. So we have the empty, so we have then the full capsids. But when we introduce those citrate ions in there, we do see that gradually we have a higher percentage of those damaged capsids, so the third peak, and also omission of the first empty peak, as well as if we look also the time where they elute, they usually elute earlier on. So this really, again, plays an importance if you want to do your QA in a stepwise gradient when you have fixed conditions for the elution and you don't rely on a linear gradient as shown here. It might be then you might be collecting a different fraction that you assume and you test it on your PD scale using a linear gradient. So definitely our answer here is that if possible, return back to the process and change the citrate buffering system with something acetate-based or formic acid-based, which do not have those interactions and do not chelate also the magnesium. Or a simpler approach, if this is not feasible, is also doing the buffer exchange to completely remove those ions and proceed then to the QA. Another case study that we'll go through is the case study on AAV8 that we've done with the collaboration of Technova, which were providers of the buffers for this study. And here we use the SO3 purified AAV, so AAV8 with a titer of approximately 7E12 and the starting ratio, so prior any enrichment of, let's say, call it 50-50%. And the idea of the case study was that we wanted to use the design of experiments approach for maximizing the resolution, the recovery, and all of the parameters that are needed for really screening the conditions on the QA. How we approach this, we use the Simultus QA 1 ml column. We collected the fraction for 5 CVs from crossing of the 260 to 80 crossing of the two absorbances. We had a set of 20 buffers, so 10 buffer A's, 10 buffer B's. And we designed the design of experiments by two different programs. So SAS GMP and Sartorius MODI. And the variables that we were testing were the buffering system. So we had a TRIS and BTP, their concentration, 20 to 50 millimolar, the eluent salt, sodium chloride versus potassium chloride, pH of 9 versus 9.5, and also the presence of magnesium, so 0 and 5 millimolar. The responses that we wanted to maximize were the recovery, the percentage of full, the ratio to 60:80 in our peak resolution, and also the retention of our AAV. For the threshold, we put that the minimum of 80% recovery is needed, and also 85% of purity. So once we've done all of the 10 runs, we added those numbers in the models, so the two models here, and this is how the model is showing its prediction values versus the actual values for jump and the MODI. And what we can see from here, that really the model, the model that it was, so the prediction is quite good for the responses of resolution, recovery, retention time, and empty full ratio. So it is quite certain in those predictions. However, both of the programs saw not a good fit. So the R square was approximately 0.4, and here 0.45. So really there is no linearity in when looking at the A260, A280 values. So what that means, that all models show good response and good fit, except of 260:80 ratio. Therefore, its reliability to predict future values, it's low. Once we accept those models, this is the responses that the two programs gave. The one on the right side, the jump, showed us that we should use 50 millimolar BTP buffer at the pH of 9. Also using the potassium chloride as a eluting agent, and that we should have a constant of 2.5 magnesium chloride in our buffer system. And on the opposite side, the MODI was really complementing those values, except for the magnesium chloride, where it said that the best results will be obtained when we have 4.7 of millimolar magnesium. So what we've done, we average those two values up, provided with the final conditions, which are stated here, and then the Technova prepared two additional buffers that would be checked. So really, if by accounting those values, we should get the responses that are predicted. So once the buffers were prepared, we also used the new column so that we confirm the reproducibility of both the column and the buffers. So we've done 2 repetitions, and as you can see here, both the repetitions do stack one upon each other. And when we looked at the responses, individual ones, if we compare the predicted values from MODI and predicted values from GMP and compare them to the measured runs, we do see that in the case of 260:80 ratios, we increased, or we were in line with the predicted values. From the resolution-wise, we got higher resolution, which is always favorable. Recovery-wise, it predicted 90% and 93%. We obtained 94% and 80%. Now, 80%, it's not really in line with the predicted values. And also it was just one measurement here, so because there were 2 runs, but looking at the profile, they do overlay one upon each other. So I think it also be, if we will redo the PCR, that the value could be different. Whereas for the purity, so we used our PETFIX system, which is using the CMAC AAV column for the estimation of empty full ratio. We obtained basically the same values as the DOE confirmed. And this is really a good approach that you really screen using the design of experiments to really screen different parameters to see how your process behaves for each individual serotype. Leaving now the QA and go to the second column that we offer for the polishing steps is the Prima S column. Again, this is the same sample that was applied. How it differs with the QA, so it's a multi-modal ligand, and it's a weak anion exchanger, also with a hydrogen bonding effect. And instead of using the ascending salt gradient, we're separating our species using the pH gradient, and usually we go from pH of 7, which is also the loading pH, and we elute up to pH of 10, whereas the the capsids do elute around pH 8, pH 9. Also, the sample should be bound at lower conductivities, and also the presence of magnesium is one of the parameters that I would screen. Last in line for the polishing steps is the Prima T column, which is also, it has the same properties as the Prima S, and also additionally it has the metal affinity coordination effect. So we designed such column that we saw that really AAV really so magnesium presence really affects the profile of the AAV. So also we designed such a column that could exploit such traits. And here for the first time, we don't see just different separation of empty capsids as we saw before, because we have empties, we have fulls, we have damaged capsids. But now we see we have 3 different populations of empty capsids, so E1, E2, and E3. And also for the first time, 2 populations of the full capsids, which the other anion exchangers did not see and saw this as a single fraction. Characteristics similar to the others, so it supports high binding capacity, more than 2E14. All of the serotypes that were tested up to now could be bound. Also, the sample loading should be with the lower conductivity, and the elution is really done with implementing magnesium gradient opposed to the sodium or potassium chloride gradient. And then lastly, we have the sodium chloride wash, where the majority of the empties elute. So really, the empties are more strongly bound to the column due to the hydrogen bonding and all the multimodal effect. For the polishing step, we will go now into the analytics part, but we will still stay on a Prima T. So there is a case study that was done on AAV8, and we wanted to screen those different subpopulations that were obtained by the Prima T. So we collected fractions that I showed before, so the E1, E2, E3, E4, E5, and we've done a couple of the analytics. The first one was the cryo-TEM, and we saw that really as we see how usually the capsids are looking, the full capsids are seen here in E2. E3 is something that it resembles the partial capsids, whereas the one with the hollow point in the middle is what is assumed as the empty capsids. The second analytics we've done was we coupled ultracentrifuge with the HPLC as seen below. So we centrifuge everything in the cesium chloride and then pumped the vial through the detectors, so fluorescence detector, which are showing here. And the initial sample in green shows our SO3 eluate. So we have some of the, let's call them heavy capsids. Then we have the full capsids, the partial capsids, which are in between the empties and the fulls, and the empty capsids. And the E1, E4, and E5 were all fall under the empty capsids, whereas the E2 and E3 are both predominantly full capsids, with this difference that the E3 also has this higher portion of heavy capsids and is also denser than the E2. Another analytics that we used was the anion exchange. So a strong anion exchanger with separates based on how negatively charged our particles are. Again, the empties fall under where the empty should elute, whereas the difference in the E2 and E3, E3 shows that there is more negatively charged compared to the E2, so it elutes later on. The third analytics was the size exclusion one. So we just tested the E2 and E3 fractions. So this is really the novelty that we saw those subspecies separation for the full capsids, and we stained those fractions with picogreen, which stains the double-stranded DNA. So the UV absorbance and the multi-angle light scattering absorbance shows the same concentrations were obtained, whereas for the picogreen, we see that the E3 absorbs more, meaning it has more association with double-stranded DNA compared to the E2. And lastly, courtesy to the refine, we also done mass photometry, and again, it showed that the E3 had slightly higher molecular mass, so higher mass compared to the E2 fraction. Those were all qualitative assessments, but also we done then the quantitative. So all of those analytics could be expressed also for the percentage of full capsids. And we do see that in E1, E4, and E5, we see, because they mainly compose of empty capsids, we don't see any enrichment steps. So we started with the 40 or 50%, depending on the analytic. But if we look at the E2 and E3, we see high percentage of enrichment, around 90%, with an exemption of cryo-TEM, where we see 76, 73. But here's also, I added a note that cryo-TEM usually gives you a readout of 3 different parameters. So one is empty capsid, one is full capsid, and then it has also uncertain species. And those uncertain species, in our case, they were approximately 12 or 16% for the E3. So I did not account them here, but if I would be added them here, basically all of the analytics would be showing the same proportions. So what was really the knowledge taken from here? The E3 fraction, which could be separated by Prima T, is denser and also is more electronegative compared to the E2. Sec picogreen shows the higher presence of double-stranded DNA. Also, it has a higher mass, slightly higher, but it is higher, and also it has slightly higher percentage of the full capsids. Last case study that we also look on today is done on the AAV9, and we compared 3 different approaches of full enrichment. So we used the ultracentrifuge, so not analytical one, but preparative ultracentrifuge coupled with HPLC, as we also saw it before, so that we have the heavy capsid, full capsids, partial, and the empties, and we collected all of those fractions. We also done the QA elution on the QA chemistry, and we collected just the full capsids, as well as the Prima T, where we collected slightly more. So also those empties were also engulfed here. And those fractions were then buffer exchanged to have the same buffer in the end. And then they were analyzed by charge detection mass spec and next generation sequencing. So what we're seeing on this slide is the SO3 eluate, so the starting material. And the interesting thing here that I want to emphasize is really, so we have a graph representing mass on one axis, and on the y-axis we have the charge. And we really see, so the first fraction here are the empty capsids, and the second portion are the full capsids. And if we look at the charge, we really see quite a big heterogeneity of the empty capsids. And if we know that, let's say, an ion exchanger separate based on the charge, this is the answer why, let's say, QA could not have 99% of fulls, or there is always some empties below our full peak, because basically higher heterogeneity of empties is evident as for the fulls. Therefore, whatever, when we're reaching those conditions, those portions of subspecies of empty will elute also with our fulls. So this is then also next in line, we have the ultracentrifuge fractions, and we see that the heavies are predominantly seen by, we have some full, we have some empties, we have some partial capsids. The one with the full, they are predominantly with full capsids. The partial fraction has concentrated partial capsids and also mostly empty capsids, whereas the empty capsid has mostly empty ones. And then we have the polishing step eluates, so the QA eluate and the Prima T eluate. We see that in the QA, we have mainly full capsids, also some other, so we have empty, partials, full, and then heavier capsids. But in the Prima T, because of the fractionation approach, we have more contamination, let's say, with the empty capsids. Still, looking at the charge differences, we see again this high heterogeneity of empty capsids. If those graphs are then summarized in percentages, and they are labeled, so let's say that we are looking at the full percentage so our full capsids, we see that same purity in regards to the full capsids is obtained by ultracentrifuge compared to the QA. So we have same proportions of fulls, partials, heavies, and also slightly higher percentage of heavies here in the QA. Prima T slightly lags behind, but really this is due to the fractionation approach, where it wasn't as narrow as on the QA. A second analytics that was also done, as said, was the next generation sequencing, and we used the long read, so really to assess how is the integrity of our capsid, of our product, and we do see that 80%, approximately 80% of reads were unique to the target, also with the read lengths that are in line with the AAV packaging format. But we always have chimeric reads. We have some residual backbone, so some residual plasmid, wrap cap, helper, and also some hosted DNA. And this is within the capsid. So this is something really to be aware of, that we don't have just one population of AAV, but we have multiple populations, as well as also different proportions of the genome. I will conclude with the scaling up. So the scaling up, really, what are the considerations for this? If we want to move from linear gradient to the step gradient, definitely we want to take control over the temperature. So increasing temperature will affect the retention and also the profile of your eluate. And do consider that when you're doing process development and then GMP suites, they have different temperatures. So do account how you will run your process to mimic those run at GMP. The pH shifts are also, we see that CMOs usually like to prepare buffers with 0.1, 0.2 pH acceptance rate, but we see differences in when we are, so we see similarities when we are within 1% difference. So to account also for that, definitely condition properly the column. So if it's followed by sodium hydroxide, you have to equilibrate it properly, otherwise your resolution will suffer, and account for any extra void volumes, so column-wise and system, so chromatography skid-wise, so to account of bubble traps and air traps. So those will all account for the broadening effect of your peak. So if you adjust your column to your system, and you're transferring everything in the same gradient durations expressed in the column volumes, if you apply the same loading amount, so milligrams of sample or per milliliter of column volume, and account for those extra column volumes, the result is really then a maintained scale up, as also seen here from 1 ml, everything up to 8-liter column. And with this, I would like to conclude my presentation and thank everyone that was also helped to do this presentation. So thank you for your attention.
Thank you, Rock, for that great presentation. We're now going to start our Q&A session. So if you'd like to join me back on camera. Hi, Rock. Great.
Hi, everyone.
So we've got lots of questions in already. My first one here for you is, can I estimate the empty to full ratio by only absorbance? That's A260 over A280.
Mm-hmm. Yeah, this is a great question. So we also went through a presentation. So one thing that really we saw is that 260 and 280 is not the best. So it is an approximation. So let's say usually we see I have 0.6 ratio. I will have my empties in there. If I'm approaching 1.3 of ratio, I have my fulls there, but it's not an exact estimation of, let's say I have 80%, 90%. So it's a rough estimation, but definitely I wouldn't base my calculation on it. So the prediction also seen by DOE that we performed, the prediction was low there. So rough estimation, but definitely no calculation done on that. Yeah.
Thanks, Rook. And is there a difference in impurity levels when using different harvesting approaches, such as lysis or secreted?
Yeah, it is. So definitely with lysates, because you lyse all of the media, also you will lyse your cells, so it will have more protein impurities in your product. So it really then comes of importance of mastering the clarification part, the pre-treatment. So I went through the TFF, but we also have the OH step we use here. We also use the simosphere, some flocculation. So different parameters that will mitigate and lower your overall protein content, opposed to, let's say, secreted AVs, where usually you don't lyse it and you have just AV that bursted out of the cells, so it will have a quite lower percentage of the proteins. So it will differ also in the processes. So those with the lysate will have more of a pre-capture step, so more effort would be needed, opposed to those with the secreted ones.
Great, thanks for clarifying that. And can I expect a difference in chromatographic profile when assessing other serotypes?
So for the different serotypes, really the best thing to do is really screen it. So I would go really a starting value. So this is also something that we can provide. So pH 9 is a good starting point. Trees or BTP based, and then using a salt gradient. But different serotypes, so the AAV9 will elute earlier on, so more of a dilution or will be needed. AAV2 also it will elute earlier than the AAV8. So definitely, every time we have a new process, a new product, we do the full screening and optimize each step. But I would say majority of the cases, so one method will give you some indications, and then you adapt those for individual steps that we went also with the design of approach here.
Great, thank you. And why can't we bind AAV at neutral conditions of pH 7 on both the SO3 and QA columns?
So the problem with why not loading at the neutral conditions is really it's down to the PI of the AAV. So the isoelectric point is around, it depends, from 6 to 7. So meaning if we load at the pH 7, the AAV won't have any charge. And if you want to bind it to the strong cation exchanger or to strong anion exchanger, at pH 7, basically it will be in the flow through. Therefore, to cation exchanger, you decrease the pH, so you protonize it, and you introduce the positive charge on it, and vice versa. You go to the alkaline conditions that you bind it to the strong anion exchanger, so pH 9, so you introduce a negative charge on it.
Great, thank you. Another question here. Based on your experience in characterization, what do you think constitutes the damaged peak? Is it resultant of the use of the CIM QA column?
So the damage peak, this is always a fascinating area to observe it. So it's always, I would say, there is not just one to blame here, but it's always, I would say, product and process related. So product related, it's always, it's part of the upstream. So how is your encapsulation going? So this is really when you're optimizing your harvesting, your transfection. So how is my encapsulation going? So a lot can be done there, and this will affect if I have multiple of subspecies or I have a manageable amount of subspecies. So this damage part is one part responsible from the upstream part, so product related, but a lot can be also done on the process. So exposure to high shear rate, let's say during the TFF, if you really restrict and have a high shear rate, you might damage your AVs. Exposure to the acidic and alkaline conditions, so below 3.5, above 9.5 pH mark, will also weaken your AAV. Those are the parameters that we want to be as close to ideal conditions to really have then control over this third peak. But I would say that it's always part of it, and always it will be there some part of the recovery. For us, we treat it as an impurity because it really also we show that it has a different characteristic compared to the main product. But yeah, it's down to the client how he wants to assess it and how also how he wants to control what its end parameter. If it's really for the toxicology studies or some preclinical, it's okay. If it's down to the manufacturing, then definitely this should be treated as an impurity.
Yeah, that makes sense. Thanks, Rock. We'll just squeeze in one final question now. Is the simultaneous SO3 binding capacity different from one serotype to another? And which different serotypes have you tested?
So basically, within our, I would say I will talk for my perspective. So for the last 6 years, I've been really just on the AAV field, and we tested all the variants. So the ones that are commonly used, and also the chimeric ones. So they all bind to the QA, whereas the capacities, they will differ really on the amount of empties versus fulls. So if we have 50-50 ratio or 30% ratio, we are doing our estimation based on the vector genome rather than the ELISA kit for the vector particles, because we see that it's more reliable, so the relative standard deviations are lower. Therefore, the capacities will be always, I would say, above 1 E14 vector genome range. Again, if we are talking vector particles, this would be 2 E14 or higher, depending on the percentages. But the point that I would define this is part of every process development. So we always do capacity testing, and we're collecting fractions of the flow through and see where the point is that we maintain the profile as it should be, so that the empties start to elute where they should, and really define these proportions to load. But I would say quite confidently that 1 E14 vector genome per milliliter, across the serotypes, it's a workable range.
That's great to know. Thank you, Rock, for answering those questions. That's unfortunately all we've got time for today, but any questions that we didn't manage to get to, we will reply via email. The webinar will be available on demand tomorrow, so look out for an email from us with the link. All that's left is to thank Rock once more for a great presentation today, and thank you to the audience for listening. We hope you'll join us again soon.
Thank you all.